There is a very ancient, perfect system of math that connects us to everything. Indeed, it unifies, defines, and identifies everything that exists. All of the math in this perfect math system here is in order, has purpose, and is in wholeness. That is, it is unified. Nothing is repeated aimlessly, nothing is random, nothing is eliminated, and nothing is chaotic. All is in perfect order. The music on this video is from the frequencies out of this math system. This math reduces all numbers to a single digit where decimals, commas, and zeros can be eliminated. Always keeping in mind that all of these do give us information. The suggestions of eliminations are correlations to some amazing concepts in sound judgment, pun intended, and knowledge. The Greek philosophers are historically credited for this math, but I think it goes back much, much further. So here we are reducing numbers to 1, 2, 3, 4, 5, 6, 7, 8, and 9. To create a single digit, all we need to do is add the numbers together. For example, 27 equals 2 plus 7 equals 9. Or 3,527 equals 3 plus 5 plus 2 plus 7 equals 17. 1 plus 7 equals 8. 8 is our single digit answer. Because of the placeholder that 9 is, any number that we add to 9 results in that number, or numbers, when reduced to single digits. 9 plus 7 equals 16. 1 plus 6 equals 7. Or we could just eliminate the 9. In the equation, 9 plus 28, for example, equals 37. Equals 3 plus 7, and that equals 10. Take out the 0. It equals 1. Or we find that we can just eliminate the 9. 2 plus 8 equals 1. If we have just two 9s, 1 becomes a regular number. 9 plus 9 equals 18. 1 plus 8 equals 9. Eliminating 9 gives the same result every time. Curiously, not only can we just eliminate 9s and 0s, but we can eliminate combinations of two-digit numbers that equal 9. We can eliminate 8 and 1, 7 and 2, 4 and 5, 6 and 3, because they all equal 9. We will get the same answer whether we eliminate them or not, every time. So 9 plus 8 plus 1 plus 5 plus 7 plus 6 plus 2 equals 5 plus 6. If we take out the 9 and the 8 and 1 and the 7 and 2, because we only have 5 and 6 left over. 5 and 6 equals 11. 1 and 1 is 2. If we don't eliminate all those numbers, we have 9 plus 8 plus 1 plus 5 plus 7 plus 6 plus 2 equals 38. 8 and 3 is 11. 1 plus 1 equals 2. You get the same result every time. When we subtract in this system, we right away have to consider 0. There are no negative numbers because there are no signs in this system. And this becomes a bona fide system. We have to change our concept of what 0 is. This is an intro. I'm going to get into this more later. Okay, when we multiply, multiplying is really, really fun because it gives us startling results right away. When we divide, we have to consider infinite numbers. Right away, when we look at these, we see that 3 and 6 have a system all of their own. It's in our face. 3 and 6 define each other, and together they define 9, always. 3 plus 6 equals 9. 3 plus 3 equals 6. 1/2 of 6 equals 3. 6 plus 6 equals 12, and 1 plus 2 is 3. See, when we always go to the single digits, we get some astounding results. 6 times 6 equals 36, and that equals 9. 3 times 3 equals 9. I love this one. 1 plus 2 plus 3 equals 1 times 2 times 3, because they both equal 6. 3 plus 4 plus 5 equals 12, and that equals 3. See, it doesn't work for the 3, 4, 5s. But it does work for 6, 7, 8. 6, 7, 8. 6 plus 7 plus 8 equals 21, equals 3. 6 times 7 times 8 equals 336, which equals 6 plus 6 equals 12, equals 3. And it isn't odd how these numbers turned around, 21 and 12? We get this all the time. These anomalies show up in such fun places. I recently decided I was going to try this with 8, 9, 1. Because, we don't go to 10, so 10 becomes 1. And what would happen if I did 8 plus 9 plus 1? It equals 9. And 8 times 9 times 1 equals 72, which also equals 9. Yay, it worked. As a matter of fact, adding any 3 numbers in order in this system, we always get 3, 6, or 9. Try it. These are the basics for the number system I'm using to deduce the unfolding of this perfect system of math. It is not difficult, but it is astounding. I originally went into this looking for frequencies to help our biosystems. I didn't expect to get this system of math as I was searching, but here it is. I started having fun with all kinds of addition and finding all these anomalies and all these really fun things happening with this addition in this system. So I decided to just put all the tables in front of me, all the addition tables. And right away we see, okay, all of the numbers are in perfect order, like they are when they're unreduced. And of course, all the numbers they're never any repeated, there's never any left out, and there's never any that are meaningless or in chaos. So that you're always going to have, when you add these up, these purple columns, which are the reduced numbers every time, you're always going to get 45, because you're always using the same numbers. But let's take a look at the unreduced numbers too. The unreduced numbers in the one table adds up to 54. You see what I mean by these? It turns from 45 to 54. And the 2 plus table is 63. 3 addition table is 72. The 4 addition table is 81. This is 90 at 5. You're starting to see this? This is 99. 108 at 7. 117 for the 8 plus addition table. This is 9 addition table, and it's 126. Did you guess it yet? Did you see it? All the numbers are the sums in the 9 times table. 45, 63, 9 sevens are 63, 8 nines are 72, 9 nines are 81, 9 tens are 90, 99 here, 108. See, they're all in the 9 times table. So this made me want to look at the multiplication tables. So here are multiplication tables, and like the 1 times tables, 2 times tables, 3 times tables, and consecutively like that. But then I started staring at them for a while, and I saw that the 1 in the 8 table they actually work together. Read with me. You read down on the 1's tables, and I'll read up on the 8th. Ready? 1, 2, 3, 4, 5, 6, 7, 8. You see how they go in the opposite direction from each other? Now, everybody knows about an octave, and I'm not going to take that away. Every musician knows about 1 and 8 being a perfect octave. So 1 and 8 seemed kind of natural to me because I am a musician. And for all musicians, 1 and 8, it is a natural thing to happen. Okay, what about the 7 and the 2? Read with me. You read down on the 2 table, and I'll read up on the 7 table. 2, 4, 6, 8, 1, 3, 5, 7, 9. Isn't that odd? 2, 4, 6, 8, 1, 3, 5, 7, 9. You see how one goes in one direction, the other goes in another direction. We're skipping numbers there. And here's 3, 6, and 9. They're kind of like in a little bubble, floating around all the systems and doing their own little thing. You can see this really clearly in here. 3, 6, 6, 3, 9, 9, 3, 6, 6, 3, 9, 9, 3, 6, all the way down. And that's what they do. That's odd. And then 4 and 5. 4 and 5 is a really fun one. But we're going to skip numbers here. So if you can find the 1 in the first column. 1, skip 1, go up 2 to 2. Skip 3, skip to 4, skip to 5 across. Skip to 6, skip to 7, skip to 8, skip to 9. Now we're at the bottom of the 5 times table. And we want to go to the top to the 1. And we're going to fill in the skips. 1, skip 2, skip 3, skip 4, skip over to the 4s, skip 5, skip 6, skip 7, skip 8, skip 9. You see how they tie each other together. So I put these together, these times tables together in pairs because you could see the pairs working here. The 4 and 5 absolutely fit together. Isn't that odd? So when I had to change the 9 on the bottom of the 4 table and on the bottom of the 7 to the top because it just seemed to fit there. It fits there perfectly, whereas on the bottom it was in the way. So no one's given me a blueprint for this, so I did put it up on top on those 2 tables, and indeed on the 8 times table as well. And the 8 times table doesn't really, as you see, fit the 9 in at all. It's just an add-on. I was looking for frequencies here. Keep that in mind. And so I thought, oh my gosh, we have pairs here. And what would happen if I wanted to get 3 numbers together, 3 sets of 3 within the 9, 1 to 9. So it would be 3 numbers and 3 numbers and 3 numbers. And those numbers, are they in a system here, hidden somewhere? Well, after staring at it, I found them because you see the 3 numbers, that would give us frequency numbers. If you have 3 sets of 3, well, you're going to get 1 number from each set, and you got to skip over 2. So after I saw it, I thought it made perfect sense. All right, let's do the 2 times table. 2, skip 2 numbers down, 8. Skip 2 numbers down, 5. 2, 8, 5. I was looking for a frequency like that because all my colleagues are really into the 5, 2, 8. And here we have the 2, 8, 5, and that was catching my attention. And let's go to the 4, skip 2, 1, skip 2, 7. Huh. Well, if you put the 3 and the 6 and the 9 together, I was really cued in by some astute people who were looking at the 528. 714 is the only thing that's left. So we just did that. 4, skip to 1, skip to 7. Now I know I'm looking at family number groups and not specific frequencies here yet. So let's go up to the 6, skip to 3, skip to 9. 3 groups of 3. Let's try it on other tables. It has to work consistently or it's not valid. So let's try the 5 times table. 5, skip to 2, skip to 8. Okay, I got the 5 to 8. Beautiful. Let's go up to the 1. 1, skip to 7, skip to 4. Yay! That works too. Okay, go up to the 6, skip to 3, skip to 9. I'm getting these same numbers all over the place. Let's do the 8 times table. And notice that it doesn't matter if we're skipping numbers like 2, 4, 6, 8, 1, 3, 5, 7, 9. It doesn't matter. We're still coming up with those 3 digits in place, those family number groups. Okay, so, and I know it all has to do with the placement of these numbers. Let's do 8, the 8 times table. 8, skip to 5, skip to 4. We're going down. You getting this? 7, skip to 4, skip to 1. We just got 2 of them. 6, skip to 3, skip to 9. Oh my gosh, they're all the way through these times tables. One more thing about this is when we add the unreduced numbers in 1 times table, we're going to get 45. It's going to be the same as the addition because we didn't change any of our numbers. It's in perfect order. When we add the numbers in every other table, we're going to get 45 also because we didn't change any of the numbers. Except for look at 3, 6. They add up to 54. Not 45. Switch it to 54. These numbers always do this kind of thing, and I find it so intriguing. Okay, so let's add those unreduced numbers. The 8 times table is going to be 360. Try to make a mental note of these because these numbers are important. The 2 times table is 90. The 7 times table is 315. The 3 times table is 135. 6 times table is 270. And the 4 times table is 180. You mathematicians must be recognizing these numbers. 5 times table is 225. I wanted to look at the 9 times table. I couldn't put it in with the other tables because it didn't have a partner. It didn't have a pair. It didn't fit in anywhere within individual tables, but I didn't know where to put it in the system yet. So let's take a look at this 9 times table. Look at the symmetry in this table. Start from the center. 45, 54. 36, 63. 27, 72. 18, 81. Isn't that odd? I took these numbers. These are all the numbers that you can notice that are just switched around. And these pairs are different from what the pairs are that we get in the regular tables. The 8 and the 3 are together because, of course, 27 and 72. And the 4 and 2 I put together because of the 36 and the 63. And 5 and 6 are together because of the 5, 54 and 45. And the 9 and 2 are together because of the 18 and 81. And I looked at them and I realized they all equal 11. And I thought that was fun. 1 and 1 is 2. They all equal 2. I thought that was odd. All the numbers in the 9 times table is, again, but these are all the blackened in ones are the sums of the addition tables. The green numbers aren't part of that. Let's look at a circled square, 360 degrees. And if you take out the 0, it's 3 plus 6 equals 9. In its square, so 4 times 90 is 360. Take out the 0, 3 and 6 are 9. The whole entire circled square is all about 9. Okay, let's look at an octagon. These angles are 135, and there's 8 of them. And they equal 8 times 135 equals 1080. You take out the zeros, 1 plus 8 is 9. Let's look at a hexagon. 120 degrees for these angles, and there's 6 of them. 6 times 120 is 720. Take out the 0. 7 plus 2 is 9. Okay, let's look at the heptagon or septagon, and it's 128.5714 is our angle, and we multiply that by 7 and we get 900. Take out the zeros, and that's not hard. It equals 9. Here's a couple more examples. I was really intrigued with that 90 degrees. That really is a magic thing going on there, 90 degrees. And all of these angles, every single angle, equals 9. Here's a triangle, and they have 60 degrees. 60 times 3 is 180. 1 and 8 is 9. This whole thing equals 9. And we already did this circled square. But I thought for the mathematicians to take a different perspective of it and look at it, it's still 3 plus 6 equals 9. Here is a pentagon with a 5-pointed star in it. Every angle in this pentagon equals 9. 36, 36, 108, 72, and the whole thing equals 9. Here we are with a summary of all of the geometry we just went through, and all of it's not even here. Like, there's not a circle in here, but I found this on the internet, and it was a good chart for me, so I put it in here. All of this geometry equals 9. So I've been having a great time and having a lot of fun with this math, even though I'm not a math person. I was just intrigued with it. And I was beginning to think, how serious should I take this math? It seems to be a really cool system. So one way I thought of validating it is to take the tables, the multiplication tables in the teens. Now, the numbers that coincide with the table should be exact. For instance, 12, the 12 times table, 2 plus 1 is 3. That should exactly go with the 3 table. 3 times the 3 times table. When we reduce all the numbers, and it does. Well, let's take 13. 3 and 1 is 4. Okay, that should exactly go with the 4 times table. So that we're not distorting anything here. We are just looking at a different system. The 13 times table goes exactly with the 4 times table. Okay, 14 times table. 4 and 1 is 5. It should go exactly with the 5 times table. 5 and 14 should go together. And they do. Okay, 15. 5 and 1 is 6. The 15 times table should go exactly with 6 times table, and it does. Same thing with the 16 times table. 6 and 1 is 7, goes exactly with the 7 times table. Okay, so I got real curious about that 45 and 54 because it keeps on coming up that they switch. And I originally put this right after it was happening. So if you remember correctly, the 45 and 54 were switching all the time. And so I looked at those side by side. And sure enough, I get all these really cool numbers that we've been getting as sums in all the tables. And it's curious, whenever I get something that repeats in here, and take notice because it just doesn't happen. 45 times 6 equals 270. 54 times 5 equals 270. And I thought that was really curious because I hadn't come across anything that duplicated like that. But if you take a look at these numbers, these are all numbers of sums that we've had in all these tables. Incidentally, there are 1,440 minutes in a day. 4 plus 5 is 9. 86,400 seconds in a day. 8 plus 6 plus 4 equals 8, and 8 equals 8 plus 1, and that equals 9. The diameter of the sun is 86,400, and that is the number of seconds in a day. This equals 9. 1080 minutes in a week, 8 plus 1 equals 9. The radius of the moon is 1,079. Well, that's pretty close. And we have to somehow come to grips with what this 8 and 9 means, especially as musicians, because the 8, the octave seems to be the ending, the beginning and end of the whole system, and yet we have a 9. What are we going to do with that? And then to 525,600 minutes in a year, and that equals 9. The numbers in the center always seem to call attention. Now, if we count from 1 to 9 and 9 to 1, we count forwards and backwards, 5 is exactly in the middle. If we count from 1 to 8, 4 and 5 are in the middle. And that makes sense to a musician too, because 4 and 5 are considered perfect intervals, the fourth and the fifth, and the octave. And either way, 5 is a very important number because it seems to be the midpoint of the entire system. Now, right away, when we do subtraction, we try to take something from something else. We try to take 1 from 1, for example. Right away, we have a 0. Okay, we have a 0, but we don't have any negative numbers. We're only dealing with whole, real numbers here, 1 through 9. And I don't want to break up the system now, so I want it to be consistent. So I just continue. I just say we're taking 1 from 2 and we're getting a 1, and 1 from 3 and we're getting a 2, and so forth. And I did all the subtraction tables because I know better than to do individual things by this time. All the tables tell us something because this whole thing is in such perfect order. Okay, so 9 and 1 seem to go together because if you read down, you read the top to the bottom, and I'll read the bottom to the top on the 9s table, and you read the top to the bottom on the 1s table. 0, 1, 2, 3, 4, 5, 6, 7, 8. Here we go again. They have partners that are exactly the same. 8 and 2. They're different pairs this time, but if you would read down from 2, I'll read up from 8. 1, 0, 1, 2, 3, 4, 5, 6, 7. The 3 and the 7 are together. The 6 and the 3 seem to be broken up here, but they're really not. I'll show you how. But 7 and 3 are paired together here because of their order. So if you read down from 3, I'll read up from 7. 2, 1, 0, 1, 2, 3, 4, 5, 6. 4 and 6 seem to go together. Same thing. 3, 2, 1, 0, 1, 2, 3, 4, 5. Now the 5, we just talked about how that was the center of the system. And here it doesn't have any pair. And it is very symmetrical. It is totally symmetrical, like the 9 times table. If you read from the center of the 5 subtraction table, 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. And 0 up, 0, 1, 2, 3, 4 up, 0, 1, 2, 3, 4 down. Okay, we never had any duplication of numbers before, and I didn't know what to make of that 0, and I didn't know what to make of no negative numbers, and I didn't think the whole thing worked. But I kept on looking at it and looking at it, and sure enough, oh my goodness, if I put a 9 where the 0 goes, everything works out perfectly. So the 1 in the 9 table is 9, 8, 7, 6, 5, 4, 3, 2, 1. And that goes up and down perfectly. So if we put a 0 always, if we have a 9 where the 0 goes, and then we reverse the numbers to their pairs, it works out perfectly. 2 subtraction table, 1, 9, 8, 7, 6, 5, 4, 3, 2. These are the paired numbers that always come up together. The 7 and the 2, and it starts out with the 8 and the 1. And most musicians don't have a bit of a problem with that, understanding that. Consider how at 1 and 8, they have so much connection that it's really easy to see. Well, maybe I'm just not seeing the connection to some of these other pairs. The 4 and the 5 definitely have a connection. So I had the most problem with the 7 and the 2, and the 7 and the 2 I finally found. But let's go on with what we were doing. The 3 subtraction table and the 7 subtraction table. You read down, I'll read up from the 7. It's going to be 7, 8, 9, 1, 2, 3, 4, 5, 6. So the 1, 2, 3, 4, 5, 6, and when you get to the 0, it's a 9, 8, 7, you go the other way. So the 3 subtraction table is 6, 5, 4, 3, 2, 1, 9, 8, 7. Does that make sense? Okay. I know this flies in the face of everything we've learned about math, but I don't know why they don't teach this stuff in school, because it was really fun for me to do this, and it helped get creative ideas, and it really is. All these were really breaking codes, and when we look at this math, we are connecting different synapses in our brain. If we rethink 0 and rethink directions, where things are going and how they're adding up. For instance, we always read from left to right. And I even read music constantly, left to right, left to right. Everything is read left to right. Well, different cultures in the world read from right to left, and I'm sure they have synapses in their brain for that. But here, it seems that, and I'll show you, this math really does induce the effort of connecting everything in every direction. So you're building all these different connections in your brain that we haven't been using. I made a grid of the subtraction tables with the 9 for 0. Okay, so on this grid that I made, if you were to take a transparent piece of paper and put this grid on it, the 9s you can pull at both corners, and you'll have all 9s folded at the top, and all the other numbers go with their pairs. Okay, 8 and 1, 7, 2, 6, 3, 5, 4. Check it out. All the numbers right with their pairs. So I was kind of thinking, are they canceling each other out? What's going on here? And like the octave, they have this link together that is discernible if you look at it closely enough. So It's not only the 8 and 1, the 6 and the 3 definitely does. 4 and 5 we've seen, they switch all the time, back and forth on each other. The 7 and the 2 is the one I had the most problem with, but that works just like the others. So I thought that was fun. So now we're gonna divide. Now think of what we're doing when we divide. We're looking at something chopped into pieces, but we have to make these pieces in order because everything we've done has been in order. Okay, so I started to divide. You have to consider infinite numbers in here. Okay, now remember, zeros aren't really zeros. Decimal points can come out. Now we have the additional thing of switching numbers, the one division table. Now, this is going to be like all the one tables were. It's all going to be in order. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's going to equal 45 in the end. Okay, so let's pair it with the 8 table because that's where I decided that it goes. Because in the end, we were looking at 8, 7, 6, 5, 4, 3, 2, 1, and then it goes the opposite direction on the other side. So these numbers are actually movements. These numbers are movements. They're not just numbers on pieces of paper. They're showing movement all the time. So when we have a number like in the 8 division table, for instance, 8, and the first one up at the top, and it's 0.125, and all of those numbers equal 19, and 9 and 1 is 10. Well, that reflects the numbers you're going to see on the outside. The lighter purple numbers. I tried to make them lighter so we can discern those numbers from the ones we generally get from adding up the numbers without changing them from the 0. So the 1 can be an 8, the 2 can be a 7, the 5 can be a 4. This is how we get the 2 different numbers for answers. Do you notice how these different numbers in the answers give us the pairs perfectly every time? Of course, because we know the secret. We know the combinations. We know the pairs now. So like in 8 divided by 3, 0.375. Well, we can add up the 375 and we can get the 15, which equals 6. Or we can do 6, 2, 4, and we get 3. They equal each other and they can be interchangeable. And right away, in the 3 reduced numbers, 963147258 or for the frequencies. Okay, look at the 7 division table. 7 divided by 1 equals 0.14285714285 all the way out. It's an infinite number. Not only isn't it in that one 7 divided by 1, it's in the whole entire table, except for 7 divided by 7. That equals a whole number, which is 1. But in every single other place, you get 2857142857114 to infinity. Now, if it's after a 0, I hear you say, we have to change those numbers. Okay, so we're going to change them. You know what they come out to be? The 1 is an 8, the 4 is a 5, the 2 is a 7, the 8 is a 1, the 5 is a 4. Do you see what it is? 2 equals a 7, 8 equals a 1, 5 equals a 4, 7 equals a 2, 1 equals an 8, 4 equals a 5. So instead of 2, 8, 5, 7, 1, 4, we're getting 7, 1, 4, 2, 8, 5. All the way out. And it doesn't matter whether you see the numbers changed or not, we're still getting these family number groups, and this information is incredible. These other tables, the 4 and the 5, they hold true to their connection, and if you look at the numbers, they're just totally in order. 6 divided by 2 is 3. 8 divided by 2 is 4. And so you get 1, skip 2, skip 3, skip 4. Now look on the outside. I put it on the outside so you can see it. 5, 6, 7, 8, 9. They all come out every time perfectly. And in the 9 division table, after the 0, then you get an infinite number of 1s. But they aren't really 1s, they're 8s. So it continues on that way. 9 divided by 2, you get an infinite number of 2s, but it's actually a 7. So the whole table is turned around. Here are the frequencies. Okay, I took them from the lowest to the highest in order. Everything is in order in this system, so it just seemed right. So starting from 147, they're the lowest frequencies, and then you get the 200s, 258 to the 285, and the 300s, and the 400s and 500s, 600s, 700s, 800s, 900s. So it looks like 9 sets of 2 in a set, or 2 sets of 9. Or it could be 6 sets of 3 or 3 sets of 6. Do you see that? With 528 and 582 being in the exact middle. And that's significant, and especially when you play it, because that it comes out of the middle and it goes into a cadence. It's really fun to do as a musician. Okay, take a look at the 285 and the 714. I put stars next to them because these are the ones we saw on the 7 division table that were just spelled out to us. And I thought they must mean something. And indeed, I think they do, in terms of what happens in the middle of this table is you have to pair the numbers. You have to put the numbers to their opposites. And the way the system is, it works out to do that. You notice how everything is in order. It has 9 hertz between each frequency, and there's always 3 hertz in between each set. And the 6s I just did because we're always doing the 3s, plus 3 is 6, plus 3 is 6. So I had the 3, 6, 9. I wanted to see where the 6 fit into the system, because it's always there with the 3. This system actually has chords in it, because I talked about cadences already. It's got to have chords. It has scales, and there is an entire system of music in here. This symbol, we call it the flower of life. I don't know if everybody's familiar with it, but I've been to a lot of ancient sites all over the world, and this is found in the oddest places everywhere, all over the world. If you think of this as a sphere, and you think of how you connect these frequencies to each other, okay? All these frequencies connect with every frequency harmoniously. It's just a matter of connecting it up. in this sphere, okay? And that's how your brain works. And it's not just a straight, flat line. It's connections that are in a 3D situation, and the different synapses go to different places. And if you listen to these frequencies and you understand this math, you're connecting up these synapses in your brain that have just been absent, or you just never use them. You know, I really, really love Beethoven. I love what we've done with our math. I love what the base 10 system and all the things we've created. But we should never lose the original concept of where everything starts. We should never lose our original math. We should never lose the beginning. Because if we do that, we don't connect ourselves up with, oh, I can go back to the original source and change it. We always have to change it from something that we know that we've been using and change it in some other little way. And I think we've been getting smaller and smaller and smaller doing that. If we can go back to the beginning, this math is not new, but I think individuals have learned it throughout the centuries, and I don't think the Greeks came up with it. I think they learned it because we taught them or they rediscovered it. But I think it is very, very, very old. I am continuing to work with this musical system. But the idea here is that how many times have you heard in your life, nothing's perfect, nobody's perfect, nothing here in this life is perfect? Well, perfection exists. It exists in the math that I just showed you. It's perfect. This is a perfect whole system. And so I'd have to say perfection does exist. Perfection is from one unified creation. And I'm saying it's one unified creation of the way energy works. The number system always showed us movement. And so the energy in that system was always harmonic, always in order. Perfection exists, and it exists everywhere.